Well, thank you very much, Martin. And I want to thank the organizers for inviting me to this meeting. It would have been nicer in person, but online is fine. I guess it's the world we live in. And this is what I'm going to talk about is joint work with Alessandro Giacomini from Brescia and Oscar Lopez Pamies, whose name might not be so familiar, from Urbana-Champaign, now at École Polytechnique. But before I start, for the first time at least in my lifetime, the long shadow of war is spreading over Europe. And for those of us like me that are over 50s, it should be kind of a reminder of what our parents have lived through, and for all of us, a real ominous moment. And in times such as these, giving a talk on this or that mathematical topic is a bit derisory. But what else can we do, right? Maybe remind ourselves that we should not, as a community, indulge in activities that may foster the folly of our species, I guess, and so I just urge us to be careful about what kind of research we do. Okay, with this, I'm going to start. So I'm going to talk about, I can't say that I'm going to talk about cavitation because that would be kind of an overkill for what I'm going to say. But let me say a few words about cavitation. So, or not. Yes. So cavitation. So cavitation is the onset and growth of essentially cavities, which is why it's called cavitation, in elastic solids, and specifically in a certain kind of elastic solids, in elastomers, such as rubber. So the first attempt at an analysis of cavitation, I guess they dates back maybe earlier, but the earliest attempt that I'm aware of is by Gent and Lindley in the late 50s. And that's essentially the viewpoint that was espoused by John Ball, in the 80s, who could kind of put it in a serious mathematical framework. And it is to view cavitation as a purely elastic phenomenon. So, so it's essentially, so what it is essentially to say, well, I'm going to have a spherical cavity that's going to grow inside an elastic material. So I'm going to look for solutions of elastic equilibrium, because this is Ball's view is a static one, in the form that I wrote here, Rx over mod x. And if you do that, so your choice is either to have an incipient defect, so that you already have a hole somehow in your domain, or if you don't have a hole in your domain, then you have to ensure that x over mod x is in your space of admissible minimizers. And so you have to have a growth at infinity of your energy, which is a function of the gradient of your field, thus imposing a very slow growth at infinity of your elastic energy. So following in John Ball's footstep, quite a few people have devoted quite a lot of energy into describing cavitation, but always looking at it from this standpoint of it is elasticity, pure elasticity, and cavitation is just geometry of the solutions to minimizing problems in nonlinear elasticity, in hyperelasticity. Now, a bit after Gent and Lindley, William and Shapley actually had offered a different vision of what cavitation. Well, I don't quite, honestly, I don't know what they did. I'm just, this is just hearsay on my part. But anyways, much later, that is in 2017, Krishnawasamy Ravichandran, called by the name of Ravi by those who know him, who's an experimentalist at UT Austin. We conducted new experiments, both poker chip and filler particle experiments, and I will talk about the filler particle experiment a little bit, on an elastomer which is called PDMS, for polydimethylsiloxane, which has a property that it is transparent, and so you can see exactly what's happening. And what he concluded is that it couldn't be purely elastic. And in particular, he looked at, he saw that cavities would essentially stretch. You would have cavities that would go from 1 micron to, or more like below 1 micron to over 1 millimeter. So a 10⁻³ growth in size. And that implies that the stresses, especially the tangential part of the normal stresses on the boundary of those cavities, are of the order of 100. And no elastic material can sustain stretches of the order of 100. So clearly, something else is happening here. So we posit that what's happening is that the new internal surfaces that are produced during cavitation have some energy, or carry some energy, or are the result of some surface energy, which itself is a product of some complex rearrangement of the fibers, because elastomers are polymers, and maybe of breakage of the crosslinks between fibers. Of course, this is just fluff in a way, what we're saying. So in any case, what this seems to push us towards is a fracture type model, which should be combined with finite elasticity and with another very essential feature of elastomers, which is that they're near incompressible. So, so what I want to present very quickly is a very naive attempt to deal with some of these features, but not so fast, because there's something else that occurs. And I want to show you a movie because it's fun to see movies, and also because it tells you the complexity. So here is an experiment that was conducted, the experiment called the filler particle experiment that was conducted by Ravi a few years ago, 4 or 5 years ago. By the way, what I'm telling you, what I'm recounting today is work that's already 3 years old, but since it's been completely ignored by our community, I thought I would talk about it. So you have essentially what's a cube, maybe it's not quite a cube, made of PDMS, which is a transparent part of this picture. And inside, you have two balls of two spheres of equal diameter that are embedded in that PDMS, and that are of a different material, much stronger. So they're not going to break or anything. And you start pulling. It's a uniaxial traction experiment. So you start pulling on them, and because it's a polymer, you don't see there are no cracks to start with, no cavities, nothing. It's pure. Here it's pure. The resolution of this electronic microscope is amazing. I don't remember what it is, and it's very close to the surface of the PDMS. And so you start pulling. So what's going to happen is exactly what I'm going to show you. So the two things are moving apart from one another slowly, and the PDMS is stretching elastically, and this is what happens until about, so it's a very long movie, so I'm not going to, until about this time. And at this time, suddenly, what happens is, you'll see what happens, you have a cavity that grows near or on or near the boundary of one of the sphere. And it's, so what it is not so clear, but there's a hole there that grows, and it slowly grows. So I'm not going to let it grow. It grows, it grows. Let me see. So it grows. Okay, so it's growing. You see that's later. It's growing, and you could say, okay, so that's some kind of cavity or some kind of crack, whatever you want. You know, this is open for debate, and suddenly another one grows, and here is now something strange that's going to happen. You're going to see immediately. So the second one will take over, and you're going to see that. So it takes over, and the first one retracts. And eventually, have you noticed that the second one, which initially was near on or near the boundary of the other sphere, has detached, it has moved, And this is what happens, and then and this is whatever it is, a crack, a cavity, who knows, and this until you start unloading, and when you unload, then you see that your thing will unload, and eventually, for all intent and purpose, just disappear. So you cannot, this cannot be accounted for with fracture, because in fracture, the idea is that the crack, once formed, remains formed and only grows. And here it doesn't grow because it vanishes and then grows, you know, and then, so it seems to be traveling on top of that. So if you were to run a fracture code, and now with the increasing popularity of phase field method, you can and the kind of Ambrosio-Tortorelli type thing, you can take the models that we've advocated for fracture and run an Ambrosio-Tortorelli type algorithm on this, and you could compute the location of the crack. At the end of the process, you would get it essentially where it is in the middle, but you would never get that evolution. So the evolution using fracture would be completely wrong. So as a first naive attempt, we got to get rid of finite elasticity, get rid of incompressibility, and focus on healing. So this is why I want to present, you know, finally, after nearly 10 minutes of rambling, a model of fracture with healing. So I'm going to forget about finite elasticity. I'm going to forget about incompressibility, and I'm going to give you the model as on the simplest possible case, which is a 2D scalar case. So what I mean is that your displacement or kinematic variable is scalar valued and depends on two variables. And I'm going to and I'll tell you why we're doing this, independently of the fact that it's easier to show the model that way. we're going to also assume, which is, I'm sure, absolutely wrong, that healing is like cracking, that it's rate independent. It's probably not true at all, because what's happening during healing is that you have a reattachment of reformation of broken links, and this should be a much more complex, there's chemistry involved, it's a much more complex process, but okay. So I'm going to assume that it's like cracking and it's rate independent. So essentially, here is a model. So let's say at some time, at a given time, you have a crack, which I call K, and associated to that crack, you have a displacement field which is elastic away from that crack in the rest of your sample, which I'll call U. And now let's say that your crack changes. So you have a competitor, a competing crack, which I call gamma. So this gamma, so first gamma may have an add length with respect to K. And in the ideology of fracture, you're going to pay a certain energy for creating more length. So I call it beta times the length of gamma minus K. But it might be also that gamma heals some of K. So when it heals, you're going to recover some energy, which will be alpha times the length of K minus gamma. And that's because I assume that healing is the same kind of surface energetic phenomenon as cracking. And now you have a new solution for this new crack gamma, which is V. And so now you're going to compare the change of total energy. So you're going to have the change of elastic energy, taking all my constants to be 1. It's going to be 1/2 of grad V minus grad U in L2, in the L2 norm squared. And then you're going to pay H1, the length of gamma minus K, but you're going to recover the length of K minus gamma. So that's what I wrote in the change of energy. And if you look at the second part, the energy, the surface energy part of this expression, then you can it's very simple. It's just a manipulation. You can rewrite it as what I wrote: alpha H1 gamma minus H1K plus beta minus alpha H1 of the add crack. And so what this seems to say is that you should really define it as energy for V, for example, for gamma, the elastic energy associated to the displacement field V, so 1/2 of grad V squared, plus alpha times the length of gamma. So that's what we're going to take. That's going to be our definition of the energy of the pair V gamma. And so this change of energy is going to be EV gamma minus EUK plus, and it's not beta that counts, but it's a difference between the cost of creating crack and the cost of, and the benefit of healing the crack that's going to come into play, beta minus alpha, H1 of gamma minus K. For those of you, maybe there are a few I know there are a few who are familiar with the Griffith way of presenting things. If you call P of L the potential energy for a crack of length L, so let's say you have a crack which starts from a point, the black dot, and which goes along a prescribed crack path, and which at time t has a length L of t. And now that crack has a choice of moving forward or healing back, but along that prescribed path. Then you can compute assuming that L of t is a smooth function of t, or of L rather, you can compute the change of potential energy associated to either the advance or the retraction of your crack L, and you assign to it a sign minus, and this would be like saying that this energy release rate, which is minus dpdl at L of t, is between alpha and beta. And it will be beta if L dot, if the crack extends, and alpha, it might be minus alpha, I don't know, if the crack retracts, okay? So
Gilles, I mean, we don't see the full screen. I think I only see beta if L dot is positive. Maybe can you move it a bit, or I don't know whether
I cannot. Well, sorry. So it says alpha if L dot is negative. I'm sorry. I can't.
Maybe it's only my problem, but I don't know.
I see the full screen.
Oh, okay.
Okay. So anyway, it's the bottom of the screen. So that's the model. So it looks like a model of fracture, but it's a bit different. And let me just say, so the result we have, and really the only result, is an evolution existent theorem. For the evolution due to, for example, a boundary condition which depends on time on the boundary of the domain, but maybe not a complete full boundary of the domain, because it might be that a crack goes up to the boundary. So you have a u of t, let's say you have, for each time, you have a crack k of t, and you have the associated elastic displacement in the complement of the crack, u of t, and u of t should satisfy the boundary condition on the part of the boundary which hasn't been reached by the crack. And then so it's in the spirit of Milke's ideology of minimizing movement. So there's a global stability statement which tells you that the energy for the solution is less than the energy for competitors, and I showed you what that one should be on the previous slide. So that's what I wrote. And then there's an energy balance which ties all the times together, and which tells you that if you add to the energy at time t the total dissipation that has occurred up to time t during the evolution, which here, and it's not completely obvious, but here will be essentially, so if it was smooth, it would be the integral from 0 to t of the derivative in time of the length of the at cracks. So that's what I wrote, but I wrote it in a weak form because we don't have any regularity in time of the crack, of the length of the crack. So I wrote it as a dissipation, as a total variation, if you want, something like that. Then you have an energy conservation, which I wrote on the last line. So Martin, if you cannot see it, but you know what it is. Essentially, that the derivative of the total energy is the work of the boundary displacement. Okay, so this is, so for those of you who haven't seen who don't know anything about fracture or energy minimizing movement, this is a bit, I realize this is a bit abstract, but that's the kind of theorem that you expect in all of those evolutions. So let me just say, because there's a large community here on whose focus is, at least in this conference, on motion by mean curvature, that it's very different here. It's not a gradient flow. So there's no gradient flow structure here. It is really a different type of evolution, but okay, maybe that's a topic for another time. So, what really, so let me, I have 5 minutes, and let me just, or 10 minutes, and let me just say a few words about how you go about proving this, and what restrictions on topological, what restrictions you have on the crack. So So this theorem is purely two-dimensional. We know nothing about higher dimension. And the cracks must be finitely connected compact sets with finite lengths. So by finitely connected, I mean that you have to impose an a priori bound, uniform absolute bound on the number of possible connected components of the crack. Let's say 27, no more than 27. So this is the same framework that was adopted for the first existence result for crack evolution, following the same kind of scheme of minimizing evolutions. That was proved by Dalmaso and Toader in 2002, before it was generalized to more, what I would call more variational settings. So this I call a topological setting. And I'm going to tell you why we are stuck here with a topological setting. And it's very different from what happens in fracture, where you don't have this kind of obstruction. And the reason is the following. So let's say you have a crack A. So the reason is that the essential ingredient, one essential ingredient, which comes at a very unusual place in the proof. It comes in trying to prove one inequality in the energy balance, is that if you have two sequence of sets, Kn and Hn, that both converge in Hausdorff metric to a set K and a set H, respectively, then you absolutely need this lower semi-continuity result, which I wrote here. And this one is fine. It's easy to prove for this kind of convergence. But it's completely wrong in another setting, a more general setting. So let me tell you why. So let's say that H, for example, Hn is H, and it's a straight line segment, H. And let's say that Kn is the same straight line segment, but divided into 2 to the n segments, and you take only 1/2, okay? And then you want to see if, so here you don't have a bound on the number of connected components, because you're increasing the number of connected components of Kn, right? And now let's say that you want to prove some version of this inequality, of this lower semi-continuity inequality that I wrote on the top of the slide. Well, what does it mean to converge more variationally? What it means is that associated to Kn, you should find a un, a function un, which is in SBV and whose jump is essentially Kn, okay? And you should be able to conclude that un, and which is such that un converges to a u, weak star in SBV, with u whose jump is essentially in the limit of, in the variational limit of Kn, which I will call K. Well, I think that you will understand quickly that K can only be the limit of Kn, the variational limit of Kn. It's kind of a Kuratowski type convergence, can only be the empty set. Why? Because if you had a point of density 1 in the jump of K, then by blowing up with a small ball around that point, essentially the jump should be 1. The length of the jump should be the diameter of that ball, but it cannot be less than the limit in for the jump of the Kn restricted to that ball blown up, because it takes only 1/2. So it would be 1 less than 1/2, which is impossible. So you cannot have this. I don't know if that was clear, but anyway, you cannot have this for a more general setting than the topological setting. Now, in terms of the proof, you essentially have two main issues. The fact that the set is K of T is not monotone with respect to inclusion means that you cannot apply any kind of Helly type theorem, which is really important in fractures, as the fact that the crack increases with time allows you to use various tricks related to Helly. And the second one, which is a problem that you have in every problem of fracture, is you need to, it comes from trying to prove the global minimality. And you need to prove that if you have a sequence UN, Kn, a pair sequence, UN, Kn, which is such that grad UN squared plus C times the length of Kn is less than, is a minimizer, essentially, for its own jump set. So that's what I wrote. And if grad UN converges weak in L2 to a grad U, Kn converges Hausdorff to a K, then you have the same inequality for the limits that you had for the UN. And in order to do that, you see the problem is the part of the jump of gamma, which is inside K, because let's say the Kn approach K from without being included in K, then it might be that K minus, gamma minus K is the empty set, but gamma n, but gamma minus Kn is all of gamma. And so you couldn't possibly pass to the limit in this inequality. So you need to transfer the part of the jump of gamma, which is inside K, to gamma n, which is inside Kn. But once you do that, then you have a Vn instead of a V. And so you need some strong convergence statements in order to pass to the limit on the right-hand side of the inequality. So with this, I'm nearly done. I will just like to show you. So let me, I'm going to show you a movie. Now, of course, a movie is not, this movie pretends to be a movie that is inspired from this model, but okay, a lot could be said. So this is, don't take it too seriously. It's a computation that shows you that adapting some kind of phased field method to this setting and doing a lot of shenanigans, you can get with something which vaguely resembles what you saw before. And for now, it's just vaguely. Okay, so whatever. It shows at least some appearing and vanishing of cracks. I have, yeah, I think I should stop here. Thank you for your attention.
Thank you very much, Gilles, for your interesting talk. And now let's open the discussion. So whoever has a question or remark or comment, please ask. So Adriana has a question or a comment. So Adriana, please.
Thank you for your talk. So actually, I have several questions, but one question is about the origin, so the experiment you have shown. So do you know whether there are, so now I ask the question, then I tell you why I ask this question, whether there are experiments in which they are able to trace the points. So the material is transparent, and then maybe are there experiments in which they trace the position of the points before and after the deformation? The reason why I'm asking this is because looking at this video, looks like there is healing of small cavitations.
Oh, I see.
And then maybe large cavitation are really the result of a plastic deformation, and they just simply close but not really heal. So
is it okay? So one thing, that's a very good question, Adriana. And one thing, of course, one thing is that, which is very strange, is that if you do a second cycle, which I haven't
exactly, this is the second question. What do you do at the second? What does it happen?
And something very strange happens. Second cycle, so after apparently all the cavities are gone, what happens is that the same process occurs again, but with a different location for the cavities.
So it's not true that the large one remains open and opens back?
No.
Okay.
So on top of this, what Ravi is proposing, but maybe it's not true, is that there's some kind of hardening due to prior cracking in the material, which of course makes it even more difficult, because how do you model that? I have no idea. But somehow, if you do a cyclic, very slow cyclic loading, unloading, you don't see cracks or cavities or whatever these are. By the way, I should say that those you see, they look like, don't think the crack is horizontal. The crack is vertical here, okay, on this picture. So when you're much further here, that's a vertical crack. It's just the effect of finite elasticity. You see a crack in its, you see whatever it is in its deformed configuration. So, you know, we have a picture of cracks, which is in our mind, which is not what it is in reality. In reality, this is, the crack here is a vertical crack. Yeah. Okay, I don't know if I answered, but.
Yes. Actually, the second question was related with the model, but I thought that that maybe, so I didn't know that the healing would occur also for large cracks. So I was wondering whether it's possible to insert in the model some threshold after which you don't heal anymore, so that you can heal only small cracks, and whether this could help the analysis possibly.
Yes, I don't think so. But you are right that there are other phenomena besides elasticity that should be taking place. And clearly it's a polymer, there's viscoelasticity, there are lots of things that are happening, you know.